Okay, let's go through some of the announcements today. Homework 2 is due tonight on Connect Math. Okay, homework 3 is up there too, so that will be due next Friday on Connect Math by the end of the day. Okay, Minitab Lab 2 is on my classes. It's due March 9th, so you can start on that one. Okay. Then we have quiz 2 today. So the topics on quiz 2 are mean, median, mode, standard deviation, and some symbols. Okay, we did a review on that Wednesday. There we go. And we have a test on the next Friday, right? So next Friday, test 1 will be not in here, but in Henson 150. I think it's near the geography wing there. This will cover chapters 1, 2, and 3. Okay, so I promised you a study guide. If you're on Zoom, it should be up under modules, but I will pass out the study guide right now. 2, 4, 5. There we go. 1, 2. All right, and let's just take a look at what this study guide kind of talks about. If you go to the first page, we just have a list of topics, okay? So if you take a look at the first paragraph, it says that test 1 will be in Henson 150 on next Friday. You will be allowed to use a calculator. You can bring your own, or if you don't have one, you can use an online calculator. Some students use like Google Calculator, that's fine. You also will use Minitab in a different window, so you'll have Minitab on the test. Okay, and the test will be on my classes. So we'll be in the computer lab together, we'll take the test, and that'll be that for the test. We have a list of topics, okay? Anything that's bolded are things that like you either need to memorize or I'll give you the formula. So if you look on the back, there's things that are bolded in italics. Those are the things that you need to memorize, okay? So for example, the population standard deviation, like taking the square root, you need to memorize, you need to take the square root, okay? Anything that's bolded and not italicized are formulas that I will give you, okay? So for example, I'm gonna give you the formula for population and sample variance. Okay. Any questions on the first 2 pages here? Okay, then on the back, I have a bunch of practice questions for you to work on, a little practice test just to give you, get you in the test mindset, give you some examples of questions I might ask. And I'll post the answers to this on Wednesday. Okay. Any questions on the test review? Okay. Oh, one more thing about the test topics and the review questions. I don't know how far we're getting into chapter 3 next week. If we don't get to like box plots and stuff, like I'm not going to test you on something we didn't cover yet. So don't get scared if like you see box plots and we haven't gone over it. We'll see how far we can get. Okay. Any other questions? All right. So what I'm going to do here, we're actually going to start class with the display off here. So we're going to see right here. Okay. And let me just make sure the board looks okay. Let's see. Okay, that should be okay. I'll start writing over here. Okay. So before we even start, I kind of want to go through some symbols that we've been covering during class. Hopefully I can find my chalk. Okay. All right. So we talked about a bunch of symbols. We have symbols that talk about the population. And then we have symbols that talk about samples. Okay, so we'll just do a tiny review here. So whenever we talk about the population, well, we need to talk about how big it is, right? So usually we use N to represent the total number of things. Total or number of things, anything like that. Okay. Okay, we also talk about the mean, the population mean. Who remembers the symbol for population mean? Yeah, I like the hand symbol, right? It's the Greek letter mu, or the U that has a tail on it. Okay. We also talk about population variance. Who remembers the symbol for population variance?
With the line over top.
Yeah, the circle with the line on top, right? Sigma. Okay. And then we talked about population standard deviation. Okay. Oh, sorry. Population variance also has a squared line. Totally forgot that. Okay. Standard deviation is the circle with the line without the square. Okay. Then we talk about samples. Sample size, or the total number of things, usually uses a small n. Okay. We have sample mean. Who remembers the symbol for sample mean? Remember?
The X with the line.
X is the line, good. Sometimes we call it X bar. Okay. We have sample variance. We take it through this one. It's S squared, okay? So you can remember it because population variance uses the Greek symbol sigma. So it's like the first letter of the Greek symbol, okay? And standard deviation for the sample is denoted by S. So a couple of different symbols we're throwing around here. But if we kind of put in a chart, it's pretty easy to like remember which symbol goes to which one. Okay. So we're on the back of like the last example with standard deviation. So where it talks about bell-shaped histograms, that's where we're on the guided notes. Okay. So let me just draw an example of that. Okay. Now we talked about ways to describe histograms and like distributions that have smooth lines here. And this one's definitely symmetric, right? If you draw a line through the center, and it's the same on the left-hand side than at the right-hand side, okay? This actually has a very special name. Does anyone remember what this is called? Well, what does it look like?
With a bell-shaped histogram.
I wonder how you figure that one out, right? Yeah. Yeah, it's called like a bell curve, right? Bell-shaped histogram. Bell curve. It looks like a bell, kind of like Taco Bell, I don't know. Looks like a bell, okay. We also call this the normal curve. Okay. The reason we call it a normal curve is because it's used like everywhere. Pretty much any single variable that deals with a lot of different factors like height or the temperature outside, things like that. A lot of those follow a bell curve. So it's pretty normal to see it. So normal curve, bell curve, same thing. Okay. Now, last class on Wednesday, we learned about standard deviation. Okay. But we didn't really talk about like why we even need to know it. Okay. So what we're going to do is we're going to take the normal curve and we're going to combine it with the standard deviation to try to see like if we can tell what percentage of things lie within some standard deviations from the mean. Okay. This is not on your guided notes, but what I want you to do is somewhere on your notes, draw 3 bell curves. Okay, with a line underneath. So one of them, 2 of them, 3 of them. Okay. And what I'm going to do here is I'm going to draw a couple like lines that represent the x-axis, but put one of the line like straight under the top, okay, and draw 3 other lines on each side. Do that to each one of these. So we have 3 different bell curves, and we have little tick marks that represent like the middle of the graph, and then we kind of branch off the middle. Okay. Special thing about the normal curve is that it's symmetric, and we talk about how symmetric graphs have the mean, median, and mode right in the middle, okay? Well, it makes sense that the median is in the middle because it's the same on the left as the right, so this is definitely the middle. The mode is the thing that happens the most, so of course the mode's gotta be up here, where it's the tallest. And the average is also in the center. So for example, let's just use the population mean symbol here. Okay, we know that the mean is right in the middle, right? So for all these graphs, let's draw a line through the center and say that the mean is there. Okay. So let's talk about what these little tick marks mean, okay? What I want them to represent is one standard deviation, okay? So maybe on this graph, the first line to the right of the mean is the mean, but we add on a standard deviation. Does that make sense? Okay. Over here, we can take the mean and subtract off a standard deviation. Okay. If we go one line out to the right of the line that we just wrote under, this would be the mean plus 2 standard deviations, right? And the mean plus 3 standard deviations. We can also do it on the left, but with subtraction. So the mean minus 2 standard deviations and the mean minus 3 standard deviations. Okay, we can do it on all of these. I don't really feel like writing it, but and just pretend I wrote it. What I'm going to do here is I'm going to draw a line on the very top graph under the mean minus 1 standard deviation and the mean plus 1 standard deviation. So I draw 2 lines that represent the mean adding on 1 and subtracting on 1. And I'm just going to shade in the area underneath what I just kind of sectioned off here. So if you were to like describe what this shaded region is, like how would you describe all the data in here? Maybe that's a bad question. The way I would describe that would be, well, everything in here is within 1 standard deviation of the mean, right? If we're over here, we're still like 1 standard deviation or less away from the mean, even if we go above or below, right? So I would call this within 1 standard deviation. Now, since the normal curve is like so common, statisticians have been like studying this for so long. And what they've discovered is that within 1 standard deviation from the mean, we actually know that 68% of the data is right in the middle between -1 standard deviations and +1 standard deviations away from the mean. Okay, so 68% of all our data points are right in the middle, right there. Okay. Any questions so far? Okay, let's go down to the second graph. Instead of drawing a line and sectioning off mu plus sigma, we're going to section off mu plus 2 sigma and mu minus 2 sigma. Okay, and I guess we can shade in our area here. Okay, how would we describe the data in this section?
Within 2 standard deviations.
Good, good. Within 2, right? Within 2 standard deviation. So now we've kind of gone further out from the mean, but we're still in the center. Statisticians have figured out that this is 95% of the data. So 95% of all the data lies right in the center between like 2 standard deviations below and 2 standard deviations above. So a lot of the data kind of lies here, right? Okay, and I guess if we do the third one, okay, and shade in that area. Oh, did I do that? Yeah. Okay, this is within 3 standard deviations of the mean, right? Okay, and statisticians have figured out that this is 99.7% of the data. So almost all of the data goes between -3 standard deviations away or 3 standard deviations below and 3 standard deviations above the mean, okay? What we just did here is we made what's called the 68, 95, 99.7 rule, okay? 68% is between -1 and 1, 95 between -2 and 2, and 99.7 between -3 and +3. Okay. Any questions so far? All right. Let's just take a look at this example now. So on the very bottom, we have that the following table presents the census projection of the percentage of the population age 65 or older for the whole state. Okay, we want to describe the data using, oh, I forget to call this, the empirical rule. Okay, so sometimes it's called the 65, 95, 68, 95, 99.7 rule. Sometimes it's called the empirical rule. Okay, so we have all this data. Okay, what you could do if you were given this on like a mini tab homework is you could literally just find the mean, find the standard deviation. I'm kind of lazy, so I use Minitab. Okay. And I found out that the mean is 13.25 and the standard deviation is 1.683. Okay, so I just use Minitab to find those two numbers because I was a little bit lazy. Okay, we want to describe the data using the empirical rule. Okay. So let's just draw a normal curve. Okay. The mean always goes in the center, right? So 13.25 goes right in the middle. If we were to draw our standard deviations, we don't need to write the symbols anymore. We can literally calculate what these numbers are. So for example, we could do 13.25 and subtract off 1 standard deviation or 1.683, okay? And that gives us 14.93, okay? We could, oh, sorry, this would be adding. Over here, we could subtract. So plus 1.683, and that gives us 11.57. Okay. So using the empirical rule, or the rule that we just figured out, we know that 68% of the data lies between 11.57 and 14.93. Okay, we could go 2 standard deviations out and do the same thing. We could go 3 standard deviations out, do the same thing. But all in all, we can create the numbers that we know that 68 or 95 or 99.7 of the data lies between. Okay. Any questions on the empirical rule? All right. For my swim meet people, I'm actually going to take a picture of the board here because the camera's not very good. So I'm kind of recording class right now. There we go. Okay. Let's flip our page now. We're going to talk about a different type of rule. And I feel like a lot of people get confused between this empirical rule, which uses the normal curve, and this new rule that we're going to talk about. Okay. So the one thing about this empirical rule is it only works on normal distributions, right? It only works if our distribution looks like the Taco Bell symbol, right? what if our distribution looks like this? Maybe like this. Something like that. Okay. Well, now it's going to be really hard to do this because we don't really know where the mean is. We don't even know if 68 and 95 or 99%, 99.7% even works, right? Okay, in this case, if we don't know it's a normal distribution, we use this thing called Chebyshev's inequality. Okay. Very similar, but it can work on any data set, no matter if it looks like this or anything like that. Okay, it's very generalized. Okay, so it says in any data set, the proportion of the data that's within k standard deviations, so whatever number of standard deviations away from the mean, is at least 1 minus 1 over k squared. So at least. Okay, now this might be a little confusing because there's just this random formula and k is kind of around, right? Okay, let's just use this distribution and try to come up with some numbers. Okay, just plug in some numbers. Let's start out with k equals 2. Okay, so what Chebyshev's inequality says is that, let's first do this 1 minus 1 over k squared thing. Okay, plugging in 2, I get 1 minus 1 over 2 squared, which is 4. Okay, that ends up being 3/4. Okay. So when we put this all together, we know that at least 3/4, right? Or 75% if you type in your calculator of the data are within 2 standard deviation from mean. Okay, so kind of like our second graph here. If we have our mean here, let's just pretend this is the mean, and we go 1, 2 standard deviations away from the mean and shade in our distribution, we know that at least 75% of the data is between this value here, subtracting off 2, and this value here, adding on 2 standard deviations. Okay, does that make sense? Okay, let's just do k equals 3 real quick. Okay, well, plugging into our formula, 1 minus 1 over k squared is 1 minus 1 over 3 squared, which is 9. Okay, and that gives us 8 over 9 or 89%. Okay, so using our rule, at least 89%, 8 over 9 or 89% of the data are within 3 standard deviations. Okay, so kind of like the third graph. If we shade in 3 standard deviations away from the mean, we get 89% of the data at least. You might be wondering why I didn't plug in k equals 1. Well, if I plugged in k equals 1, I get 1 minus 1, which is 0, right? So Chebyshev's inequality doesn't really work for 1 standard deviation away from the mean, but we can do k equals 2 and k equals 2. Okay. So for the test, you can either memorize this formula and plug in k. I think that's kind of useful. If it gets a little confusing for you, well, the most popular ones are 75% and 89%, right? So you could literally remember that 75% of the data are within 2 standard deviations, while 89% are within 3 standard deviations. Okay. One more thing, the difference between Chebyshev's and the normal curve is Chebyshev's inequality uses the word at least. The normal curve uses the word approximately. Okay. So very small difference there, but make sure that you're using the word like at least for the Chebyshev's one, approximately for the normal curve. Okay. Any question on Chebyshev's inequality? Okay, take a picture of this. Yeah. All right. Okay, let's just take a look at the one Chebyshev's inequality example here. We have a public health study. We're looking at systolic blood pressure measured for a large group of people. Their mean was 120, standard deviation was 10. Let's see what Chebyshev's inequality provides us about the data that represents 2 standard deviations away from the mean. Okay, so I always like to draw a picture. We know that the mean is 120, right? Okay, and the standard deviation is 2. So let's just find the 2 numbers that lie within 2 standard deviations away from the mean. Okay, well, let's just add first. If we do 120 plus 2, which is our standard deviation, we get 122, right? So this is 1 standard deviation away from the mean. We can also add 2 again, 124. Now we're at 2 standard deviations above the mean, right? If we go below, we get 1. I'm really bad at mental math, so don't judge me, but 118, I think, yeah. And
So, sorry, but what are you doing between each one?
So this is the mean, right? I'm trying to find what 2 numbers are within 2 standard deviations away from the mean. So this number here is 1 standard deviation above the mean, right? I just added 2, which is the standard deviation, to 120. And then here we are 2 standard deviations above the mean. Okay. Now going below, this is 1 standard deviation above the mean. And I'm not going to write it this time, but I think 1, 1. Oh, I'm sorry. The standard deviation is at 2, right? The standard deviation is 10. Is that why it's confusing? Yeah. Okay, yeah. Sorry about that. I read 2 and I didn't realize that there was another number there. Okay, this is where you know me. I make stupid mistakes everywhere. So I made a fatal mistake, which is not writing all the information on the board before I started doing the question. So let's just write this out. The mean is 120. And the standard deviation is 10. Okay. Now we can start doing this. Okay. The mean is 120 still. 1 standard deviation above the mean is 120 plus 10, which is 130. There we go. Okay. 2 standard deviations would be 140, right? If we go the opposite direction, we have 110 being 1 standard deviation, below mean. And going even farther, we have 100, right? Okay. So using Chebyshev's inequality, we want to know about 2 standard deviations away from the mean. Well, that's this one. So we already figured this out. So all we can say at the end is we know that at least 75%, right, k equals 2, of the data lies between 100, which is 2 standard deviations below, and 140, which is 2 standard deviations above. So 100 and 140. Okay. Any questions on this example? Okay. I promise to write down my stuff later on, so we don't have to think about this anymore. Okay. All right. Let me take a picture of this. There we go. All right. Let's go on here. Our next definition is called the coefficient of variation, or the CV. So sometimes we're interested in comparing the mean and the standard deviation, but like combining them into one number, okay? And this is where this coefficient of variation comes along, okay? Very simple formula, sigma over mu. So this is the population standard deviation, and this is the population mean, okay? So if you're asked to find the coefficient of variation, you take the standard deviation, divide by the mean. Let's just kind of talk about this real quick. Okay, if this equation here, the coefficient of variation, if this is a big number, do you think it's more spread out, or do you think the data is more close together? So if we have a big coefficient of variation. Small, let's just think about it. The standard deviation tells us how spread out things are, right? So if the standard deviation is really big, we have a really spread out data set, right? And if the standard deviation is really small, we have a very close together data set.
Would it matter like how big the mean is? Like say the mean is 120, but the standard deviation is like 2.
I would say maybe we're comparing two things with the same mean. How about that?
Okay.
Does that make it more?
Okay.
Yeah. So if they had about the same mean and we had a really big coefficient of variation comparing like two different things, we would have something that's more spread out, right? So more spread out, okay. And if it's smaller, we can kind of imagine it either having a really big mean or more close together, right? Okay. Usually our means aren't like too extreme, so that's kind of why we're thinking more about the standard deviation here. But I do like your point about it depends on the mean. Okay. So we have our formula for the coefficient of variation. Okay. Let's do a little example here. Okay, so I'm going to take a picture of this. Yeah, let's do a small example here. So okay, so this example talks about the National Weather Service. They're recording over a 30-year period the annual precipitation in Atlanta, having this mean, standard deviation, annual temperature, and the annual temperature. Okay. Okay, so over the 30-year period, it had a mean of 49.8, standard deviation of 7.6, and that was the precipitation. There we go. And then we have temperature that has a mean of 62.2, standard deviation of 1.3. Okay. Now, to prevent myself from making some dumb mistakes, what I'm going to do here, and I recommend it for you too, is to write down all the information that we're given instead of like trying to solve it automatically. Okay. So we're given two sets of data. Precipitation, I can spell it right. Okay. And we're also given information about temperature. So I'm going to make a little chart, and we're going to like figure out what the mean is, what the standard deviation is, so we don't have to go back and like read it again. Okay, so mean uses this symbol. This uses that symbol. So what is the mean of the precipitation? 49.8, good. What about the standard deviation? 7.6, right? Okay. Then when we're given the temperature information, the mean was 62.2 and the standard deviation was 1.3. Okay, so now I have my little chart. I don't have to read the question again. I have everything I need on my paper or on the board. Okay, let's find the CV, or the coefficient of variation of the precipitation. What would I do to calculate this that way? What would I divide?
The standard deviation by the mean.
So 7.6, right? Over 49. So I guess the CV, I did this in my calculator. I got 0.1. Okay. Then we can do it with temperature, right? So CV of temperature. Well, that's got to be 1.3 for the standard deviation of temperature over the mean 62.2. Okay. I did this in my calculator and I got 0.02. Let's take a look at these two numbers. Now, the means of the precipitation and the temperature were about the same, right? So there's really not much difference in the means. But now we have a really small coefficient of variation of the temperature and a little bit larger coefficient of variation of precipitation. So which one, temperature or precipitation, is more spread out? Which set of data is more spread out, the temperature or the precipitation?
Precipitation.
Precipitation, right? Because this one is bigger. And it actually makes more sense, right? Precipitation is more fluctuating, right? Temperature kind of stays the same over 30 days. So I think this result actually makes a lot of sense to me.
This video is sponsored by swimming. Swimming is the sport or activity of propelling oneself through the water using the limbs. Go in the pool and jump in. Start swimming like this guy. He's having a great time. Also, good luck to the SU swim team during their meet this weekend. Okay, bye.